Okay, what I'm going to talk about today is actually solving a strongly disordered x-axis model by using perturbation theory. Our aim in this work is to identify bound of the information spreading velocity or speed. Okay. So here's the outline. Okay. Is it? Oops. Okay, let's just move in. Okay, here's the outline. First, I'd like to introduce the difference between the many-body localization and Anderson localization very briefly. Since our aim is to investigate the information spreading, I'd like to introduce one of the tools to study information spreading, which is called OTOC, out-of-time ordered commutator or correlator. And then I'll come to the my own questions about this information spreading in MBL. Is namely, can we go beyond the effective description of effective Abel model in a more realistic MBL system? And what about the issue with the two-dimensional MBL? That's my particular question in this talk. Okay, and then I'll proceed to my method, a perturbation method to compute OTOC in weak hopping regime with a very strong interaction. So here, laser pointer is not very working well. Okay, I'll use the mouse. Okay, this is the regime we are considering. So ZZ is interaction parameter, which is sort of the unit energy in our system. And disorder field strength is much stronger than the interaction, and hopping J is much weaker than the interaction. The main result would be is that we identified the fastest and slowest scrambling in the system, which corresponds to the upper bound of the spreading speed, and the lower bound of the propagation speed. And this feature actually survives in two-dimensional system. So we show some evidence of the slow information spreading in 2D system as well. And that could be a signature of 2D MBL. Although some theorists said it is not possible in infinite system, but we are considering the finite size system. Okay, so here's our model, the Heisenberg XXZ model in 1D. Let me just go briefly what these terms means. The first, without this G-man field, it's just the usual the Heisenberg XXZ chain. There's a two important ingredient to cause the many-body localization. The first one is disorder. So it has the G-man field here, which is the difference over every site. So by increasing this field strength, so Zi is random value between -h to h, you can make some kind of transition to MBL. When h is very small, it stays at the chaotic phase or thermal phase, but you increase the strength of the disorder, and you will see some feature of the MBL. Whether it's really a true transition or not is kind of under debate right now. But at very strong field, at least in 1D system, there is a very well-defined signature of the many-body localization. And the other ingredient is interaction. Without interaction, it's just Anderson localization. So interaction term here is the JZ component here, which is exchange interaction. In terms of the particle language, if you transform this Hamiltonian to particle Hamiltonian, this JZ plays a role as a particle-particle interaction. And why this is essential is because it causes some dephasing, which is the source of the information spreading. So because of this interaction, it makes certain difference between from the Anderson localization. If you measure this information by using entanglement entropy or out-of-time ordered correlator that I'm going to introduce in the next slide, you can certainly define the velocity of the propagation. So in ambient system, it turns out that the information spreads in logarithmic time, while in chaotic system, it's linear in time. So that's the difference. And in Anderson localization, without the interaction, everything is frozen, so information is not spreading at all. Let me go through the OTOC very briefly. The OTOC is one of the tools to study information spreading or information propagation or information scrambling, if you prefer to say. And it's defined with these two local operators. There's another way to explain the meaning of the OTOC, but I like to use the squared commutator. So if you prepare this local operator here at distance r or x, and if you make one of the two operator time evolve, then because of the interaction, this operator expands in space. So at some point, those two operators are not local anymore. It has certain overlap. So that can be measured by this squared commutator. And that's one of the definitions of the OTOC. And it's directly related to correlator form here. The out of time ordered, the name of the meaning of this name is actually coming from this form of the correlator, because time is not flowing in one direction. And this OTOC is closely related to the more familiar concept, namely the Lieb-Robinson bound. So in chaotic system, you can measure the operator norm of this commutator, and it's proven that it has a certain bound with the exponential of this form. It means that if you check the constant, if you put constant on this term, you can draw this kind of the light cone. So the commutator is very, very small here, but it grows quickly once you get through this, this line. So it's linear in time, and it's called as the light cone here. In ambient system with interaction, this form is modified because of the dephasing effect. And it's written like that. So exponential form is here, but there is a t in front of that. If you observe this t in the exponential factor here, then it becomes logarithm of time. So light cone is changes in logarithm scale of time. So that's why we call logarithmic light cone here. And that's because the exponentially decaying interaction that I'm going to talk about in a few slides. To explain this logarithm light cone or logarithmically slow information spreading, the key concept in effective model is local integrable motion. So if you diagonalize the Hamiltonian, and if you and then you can somehow define this the unitary transform of the local operator, and then you can transform this operator into some constant of motion in ambient system. So the eigenstate is defined in space of this local integrable motion. Using this local integrable motion, you can rewrite the Hamiltonian in this form. And then it looks like very, very classical because it has only G component here. But what's special here is that it's all-to-all interaction system, even though the original system is short-range interacting system. So there's a Jij or some K terms for the multi-spin interaction. This interaction can make some effective interaction between two distant rhythms. And if you search it, and it looks like the exponentially decaying form with some length scale. So the effective interaction between the two rhythms has this exponential form. Then time scale of some dynamics happening there is naively as one of the effective interaction like this. So if you plug in the exponential -8 slash chi xi, then you will get some logarithmic time happening in this relation. So it's very, very naive logic, but actually you can see it more explicitly if you compute the OTOC with this, the Hilbert Hamiltonian. You can calculate it exactly because this is sort of the classical Hamiltonian. If you assume that this timescale xi is very, very well defined in this system, you can just compute it, and final form of the OTOC in correlator form is written like this. So there's a explicit exponential factor here in front of t. There's a t in front of this exponential factor. So if you plug in some constant, if you find some t that gives constant of the order of unity of the correlator, then you can define the light cone. And it's easy to see is why called the logarithmic light cone in this relation. If you just take logarithm in front of the both term. But there's a catch. The catch is that I said in this calculation, we have very well-defined length scale, xi, but that's not true. In the definition of this, in the building process of this effective Hamiltonian, the decay length xi is actually varies over the eigenstate. So if you try different eigenstate to compute the effective interaction, that gives different xi. In terms of the light cone, it means that the slope is actually dependent on the eigenstate that you try to measure the information spreading. In other words, speed of the information propagation is dependent on the eigenstate you try to measure it. And in realistic system, more realistic system, that could cause some large deviation in calculation of OTOC. Maybe it looks like this. So it's some work in 2017. And as you can see, this is the color plot of the OTOC measured. It has very, very broad range of the changes from 0 to 1. So what we want to study in this respect is whether there's some kind of the structure here or not. So we found that it's actually very highly structured, but it has some rule to generate it. And that's how we define the two bounds of this light cone corresponding to fastest and slowest mode of the information propagation. And the other issue that I'm going to consider here is the possibility of having many-body localization in 2D. What I mean by many-body localization is not a proper phase as in the phase transition, but it's more like a property of the some system. So here's a previous calculation of OTOC in two-dimensional system, which is bosonic system. And they mapped their Hamiltonian into Hilbert form, and they calculated the OTOC from the Hilbert Hamiltonian. It looks like logarithmic, right? And there's other evidence of the 2D many-body localized the state in experiment and numerics. Most of numerics is done by the tensor network calculation and in finite system. But there is a strong objection of the existence of many-body localization in 2D in infinite system. And they said some avalanche happens in this system. It propagates really quickly. So one part of the system is thermalized and it spreads eventually. And anyways, we want to address this issue within our own calculation. And that's how we calculated OTOC, which is the construction of the perturbation calculation. This is the x-axis Hamiltonian that I showed you before. To compute energy out of this Hamiltonian, we divide this Hamiltonian into two parts, unperturbed and perturbed. Unperturbed Hamiltonian is here, just Ising chain with a disorder field here. And perturbation is this hopping term. If you rewrite this term, it's just a hopping of the spins. Okay. And in some view, you can say that this perturbed Hamiltonian is completely localized in Fock space. So it's sort of the Fock space localization. And if you turn on this Hamiltonian, and then it makes hopping between these Fock states. So if you start one Fock state, and if you turn on the Hamiltonian, you can go the other Fock state. And if you assume that these non-zero hopping and zero hopping is connected adiabatically, you can consider this Hamiltonian, this perturbation calculation works. And I believe that's valid in some limit of the weak hopping and strong interaction, because there this perturbation is very small and the energy spacing in unperturbed Hamiltonian is large enough. So, and in detail, the OTOC is now written like this. Probably I don't have time to go through all. So I just point out some important things only. So in OTOC, what's important here is that in our regime, it's written with just one component of frequency and time. There's just one cosine term. And this frequency, omega, alpha, beta, gamma, delta, is frequency of OTOC measured at a specific eigenstate that you gave here. And then in this limit of strong and weak hopping, strong disorder and weak hopping regime, the beta, gamma, delta state is uniquely determined. So what you should do is to compute this frequency by using the energy corrections at this particular alpha, beta, gamma, delta state. And it's all dependent on alpha. So once you pick the alpha, then beta, gamma, delta is just determined. And you can do it with numerics. And it looks really horrible, right? So in this case, we don't have diagonal term in this order. And that means that only even order survives. The even order, the correction is written like this, which is very horrible, but it's actually known from the 60s and 70s in quantum chemistry. And if you compute it, you get this picture. So let me explain this picture. This black dot here, circle, is exact diagonalization results. So if you go through all eigenstate to compute out the OTOC, and you will draw this kind of figure after the disorder average. Then you fix some value for OTOC, and you can get some time. And the whole picture doesn't depend on which value you pick for OTOC, OTOC, but this T star is now given for every eigenstate. And these eigenstates are grouped in this figure. So there are a lot of eigenstates, but it goes into one of the four dots. And you calculate the same thing with perturbation theory, you get this plus sign, plus marks, with just a non-zero lowest order. So I would say my perturbation calculation works really well. But what's interesting in physically here is that there's some structure, which is unexpected. So in view of the Elvin model, this is related to the eigenstate dependence of the length scale. And somehow, well, if you don't have any knowledge on that, probably you will assume some kind of the very smooth distribution of it, but it's not. Well, in our limit, it's very, very discrete. To understand that, we look back our perturbation calculation. So in perturbation theory, the non-zero lowest order occurring at the n, which is function of r, presumably. And then you will have this kind of logarithmic right cone, right? Because it became an exponential form. And this lowest order perturbation is tabulated like this. So if R, which is the number of the spins between those two operators, if the R is 4, there is only 3 possibilities, 4, 6, 8, and etc. And if you look at this table, you can find some rule here. If you just look at the highest order, highest non-zero lowest order, then it's just twice of the R, the 2, 4, 3, 6, 4, 8, something like that. And if you try to find the lowest one, the smallest one, only for the even R's, it's just R. When R is 2, you have the second order perturbation as the lowest non-zero term, and 4 is 4, and 6 is 6, something like this. So you have very, very definite bound of the right cone. So from the slope, you can compute the smallest velocity that gives you this light cone, and that one gives you the highest velocity. So I would say this is fastest scrambling mode and the lowest scrambling mode. And actually, those numbers in the table can be formulated like this. So let me explain this very briefly. Since the lowest order perturbation comes from the string of the perturbation operators that connects this part and this part. If it's not connecting this part and that part, that gives you 0 contribution. And then lowest order comes from the minimum number of the perturbation operator to bridge these two dots. And if you have this kind of the 0-1 pair, the up and down pair, then you would need just one perturbation operator to flip it, because it's the exchange operator. This hopping operator, it flips those paired spins. And this single ones, to flip this operator, you need to move this one. So it has one perturbation operator, and these two paired, staggered pair, you need just one operator. Then you can count the lowest order in this form. So we understood what configuration makes this bound, and what particular configuration makes this bound. So the upper bound of light cone, which corresponds to the slowest scrambling. To get this one, you have to have all spins aligned between these two parts. So it gives you 2 possibilities, or up and or down, ferromagnetic state. So you can, if you try the ferromagnetic state, you will get the slowest information scrambling. For this one, you have to have the staggered spins filling out the space. That includes the antiferromagnetic state. If you try the antiferromagnetic state, and then you can get fastest scrambling. That's the lesson from the perturbation theory. And unfortunately, we can calculate the slowest scrambling case in closed form. So you can compute, it's very messy calculation, but if you consider the diagrams of the perturbation, you can somehow get this very nice formula. So this is closed, since this is closed form, you can get very, very large R to test this light cone. Just let me explain the meaning of each term. It's a combination of E alpha, E beta, and E alpha and delta. Since alpha is the unperturbed state, it doesn't have any correction because it's all empty. There's nothing to move. But if you have the one excitation here, then this spin moves to the other part and it should come back to complete the perturbation term. That is here. And E delta term also has one excitation in the other part. It should travel like this, and it makes this term. If you have 2 excitations, which comes from which appears in the E gamma term, then you have to move both spins, but it should meet at some point. And that gives you this kind of contribution. So if you compute this frequency with this closed form expression, you have this, the frequency have some scaling. So there's a z over h to the r contribution here, which means that the length scale in terms of effective interaction is one of the logarithm of this part. So how many minutes? 3 minutes, okay. So it has that one. And if you compute the distribution of the omega, and now it's well defined, meaning that if you increase r, and in this scaling of this one, you have very sharp transition from 0 OTOC to 1 OTOC. So the light cone is really well defined here. For the lower bound of the light cone, corresponding to fastest spreading, the analytic calculation is not possible, but the lowest order perturbation, the configuration gives you some way to write an effective Hamiltonian. Since it's all the staggered spin and your perturbation just flip the paired spins, you can actually decrease this whole Hilbert space into much reduced one with half of the spin's length, half of the system length. So pair spin gives you one like pseudo spin. So the here there's a 6 spins. For this six spins, you only need 3 spins to describe the lowest order perturbation. So you can rewrite the effective Hamiltonian, and you can calculate the much larger system. Then you can get to with exact diagonalization. In this case, scaling is a little different. So it's not j over h, but h to the kappa, which is very close to 1.5. Okay, and if you look at the probability density distribution, it's all well defined as you increase the distance between two operators. So in that case, also, the light cone is well defined. So I don't have much time, but let me briefly mention about the higher dimension case. Well, probably easiest geometry of the higher dimension would be the beta lattice. In beta lattice, if you pick this site and that site to compute the OTOC, the path connecting these two dots is linear. This is just chain, so nothing changes. So our calculation that I've shown in previous slides applies to this beta lattice, and you will get linear light cone. Then the question is square lattice. In square lattice, there is a lot of possibility. But let me just focus on the lowest possible light cone and the upper light cone, corresponding to 2 limit of the propagation speed. In case of the antiferromagnetic state, that gives you fastest scrambling. If you consider how the perturbation operator flips these spins, then you will see it's basically a chain. So if you pick this root and to recover to make a full string that appears in the perturbation, it should be exactly coming back from this root, along this route. So it's just a summation of this root. So I would say this scaling doesn't change this, and light cone is still linear. The ferromagnetic case, I don't have very definite theory to explain it, but it seems like that it's also a summation of the chain contributions. So this is our full result. This is the OTOC computed, this light cone computed in the 2D XXZ model. And the plus is exact diagonalization result, and the circle is lowest order result. It all gives you a very well agreed result and looks very linear, at least to me. And in case of the antiferromagnetic state corresponding to fastest scrambling, it's all linear as well. In that case, exact diagonalization is not possible. So we just did numerical perturbation theory calculation up to the fourth order. I mean, the four lowest non-zero perturbation terms, which agrees very well. So in summary, we have studied some perturbation calculation to compute OTOC, and we found the very, very highly discrete structure that gives you the lower bound of the propagation speed and upper bound of the propagation speed, and that also applies in 2D. That's all. Thank you.
Okay, thank you. Thank you very much. Thank you very much. Very nice talk. Do you have a question or comment?
Yeah, just a quick question. How will this bound look like if I take an integrable interacting many-body system, let's say an ordered, maybe even one like the Hubbard in 1D?
I don't have definite answer, but I believe you have very, very similar structure because there's other studies of interacting system, and they said they found some features very, very like MBL feature, and that include the logarithmic light cone. So,
and if I naively take the non-interacting, but many-body but non-interacting disordered Anderson problem, what will happen then?
Well, if it's just a usual Anderson type of model, it won't give you any kind of propagation. But if you consider a very, very specially designed system, like in the so-called disorder-free localization, I think you will have very similar feature.
But still coming back to the Anderson case, I mean, I still have exponential localization of single particle eigenstates, so I still have a localization length, so I could try to apply again your argument. So what is going wrong here? Because you say there's no spreading.
I don't get it.
Okay, maybe we talk later.
Yeah.
Okay.
Thank you.
Yeah, we have one more question. Do you have one? Do you have a question? Okay, if not, then yeah, time's done. So let's thank speaker again.